Today, I have Randy Ruth. Randy is the Executive Vice President of our company. Randy is involved in engineering solution sales. He's a friend and a mentor to me, and a friend and a mentor to many of us at Eastern Controls. Little known fact, maybe for a lot of people at Eastern Controls who haven't been there as long as we have, Randy's been here for 37 years, and I've been with Eastern since 1997. I think I was Randy Ruth's first hire when he became the sales manager. So, Randy Ruth, welcome to my podcast.
Thanks, Bill. Yeah, it's great to be here. Thanks for the opportunity to talk a little bit about something that I have a great passion for.
Hey, and speaking of passion, that's what we're here to talk about, right? You and I are very passionate about the business. And and you solve problems with a lot of our different product portfolio, working with guys like me to help us out. And one of the most interesting products in our portfolio, and really very uniquely designed from an engineering perspective, is the Mason Lincoln Log. The Lincoln Log is it's reliable, it's cost-effective solution, and it solves problems in cavitation and erosion. And in my career, the ones that you and I've worked on mostly have been with cavitation, but I know there's erosive applications where it helps as well. So, Randy, I know you got a few slides. Folks who are checking out this podcast, listening, this is going to be a really strong presentation, a strong message about cavitation erosion. The Lincoln Log's unique. And let's hand this off to you, Randy. Let's talk about that Lincoln Log control valve with Mason Young.
Okay, great. Thanks, Bill. Yeah, as I say, there's a real passion here because over the last few years, I've really concentrated on looking at these problematic areas. At Eastern Controls, obviously, we want the customer experience to be a pleasant one, and our business has been about solving problems, looking for those pain points that the customer has. And this particular problem rears its ugly head quite a bit, predominantly in the power generation market. There are other markets in oil and gas, but the high pressure liquid letdown application and what customers have been forced to live with has been very much problematic for our electric generating customers. They're under the impression in a lot of cases that because it is such a severe application, high delta Ps, that what happens with their valve is just going to happen and there's nothing really that can be done about it. And every 6 months, every year, every other year, when they have their outage, they get into these particular valves, which we'll talk about, and end up replacing the trim due to cavitation. So we wanted to talk a little bit about the fact that you don't have to live with that. We have a solution. We can take that very severe application and turn it into a fairly benign application with the Lincoln Log.
Yeah,
So
Randy, let's just real quick. You talked about those power plants, for instance, and you and I have been down that road in those conversations. You know, a lot of times a power plant will sit there and say, well, you know, hey, yeah, we replace the trim every year and it's costing us 20, 30 grand or that. And they just kind of think, well, that's just the way it is. And we've shown that the Lincoln Log can solve that problem and they're not replacing that trim every year, correct? I mean, that's kind of one of the things we do.
Yeah, I mean, absolutely. The whole story is that we can eliminate that high maintenance issue. We can put that valve in, and in many cases, 10, 12, 15 years, the valve's not touched in any of those outages. So again, just taking that severe application, and we'll talk a little bit about what the conventional means of solving cavitation might be and how the Lincoln Log differs. So I think initially, Bill, it's to understand a little bit what's happening in the valve and what causes cavitation. I have a couple slides here, so let me just bring it up. Hopefully you can see that okay.
Yeah, Randy, I can see it real well, which means folks watching this podcast can see it. So rock and roll, man, go.
Yeah, so real quickly, obviously a control valve is a variable orifice, and inside that valve, what's occurring, we're going from an upstream pressure to a desired downstream pressure that can be dictated by the application. and in this case generally is, there is a point where the hydrostatic pressure drops to a point we refer to as the vena contracta. So that vena contracta is the point of lowest pressure, but also highest velocity. And then there is a recovery of pressure to P2. Cavitation occurs when that vena contracta drops below the vapor pressure of the fluid. And in this case, that's what this little illustration is showing, and then recovers above P2. So what happens when the pressure drops below vapor pressure, even momentarily, there's a formation of bubbles. Those bubbles contain steam and gas. And when they recover above the vapor pressure, all those little bubbles that were formed then become, they actually end up imploding and become microjets of energy. So I don't know if you can see that, but the bubble formation now are going to collapse and implode on themselves. But what happens is the velocity that they're moving at creates a tremendous amount of damage to the existing metal in its way. So in the case of a control valve, it can be the plug, it can be the seat, it can be the globe body, it can be the piping, depending on the velocity that that the fluid is moving at.
And if I could, sorry, you and I have done this many times, talked about cavitation and control valves and Lincoln logs. It sounds like marbles, right? I mean, that implosion, right? So, I mean, I've literally been at plants, and it sounds like marbles going down the pipe, doesn't it? It's pretty unique, correct?
Absolutely, yeah. I mean, there's potential for vibration, and but definitely the sound that's created. I remember the first time I heard it, I was like, that can't be water going through that valve. It sounds like rocks, and that's a classic sign that there's cavitation occurring. It can be different degrees, obviously, based upon the pressure drop. And one of the things that I didn't mention on that first slide is that pressure recovery in the valve business, we refer to that as the F-sub-L, the pressure recovery of the valve. And that recovery is different for the various types of valves and geometry of those valves. And that plays a major part. And you'll see when we talk about Lincoln log as to how we handle that pressure recovery factor. So again, Wolfie, I know this is in some of these presentations we do on Lincoln log, and solving these problems are 1 hour, 2 hour presentations. This is kind of just a taste of what this is about.
Well, yeah, exactly right, Randy. So, you know, what we're doing in today's podcast is give customers a taste of this technology. And yeah, if folks want to learn more about in more detail, obviously we're looking for them to give us a call and go into it. But I know you got a few more slides that are pointing out the Lincoln log. So why don't we go there?
Yeah, just further to the cavitation, I mentioned
Please.
that the metal gets destroyed by the implosion of these vapor bubbles when they recover above vapor pressure. And this is a classic example of what cavitation looks like. It's very easy to identify. Sometimes people will think they've got erosive conditions. There's a distinct difference between the way the metal gets destroyed from erosion versus cavitation. It's very jagged, non-uniform, as if someone took a pick and just ate away at the metal. So this is an illustration of a cage-guided balance plug valve that was the corresponding cage and plug. And you can see how the damage, and obviously that valve's not going to shut off too well as a result of that damage. There's a lot of ways that people consider how to solve for cavitation. The most conventional way is with a drill hole cage type design, and we at Mason-Neal make this particular design as well. And in this case, what we're relying on is we run the valve in a flow to close configuration with the process going through a series of these small holes. And the reality of is what we're trying to do is get those bubbles to implode on themselves inside that cage away from the metal. And this is a very effective way of containing cavitation. In pressure drops, kind of rule of thumb, up to maybe 800 pounds. And in these applications in the power plant, where we see feed water level control valves on a high pressure boiler of, 2,500, 3,000 pounds of pressure drop, recirc lines or min flow lines where we've got, again, 2,500 to 3,000 pounds of pressure drop, the drill hole cage design is just not effective for containing that cavitation. So the valve that we wanted to talk about, and I don't have lots of slides. This is the only slide I'm showing on what the valve actually looks like. But this is our Cadillac. This is the valve that's going to come in and solve all those high pressure liquid letdown applications, including a temperation, as I mentioned already, feed water level control, recircs, any place where we're talking pressure drops in excess of 1,000 pounds.
Hey, Randy, if I may jump in real quick, you mentioned power plants for Lincoln Log and high letdown applications and feed water applications. You and I have also worked on Lincoln Logs at places like refineries, and occasionally like chemical plants and such have some challenging valves as well too. So I'm just curious, just off the cuff, this, again, it's a podcast. This isn't like a rehearsed type of thing. Have you done applications outside of power plants? Like, have you done applications? I know you've done refining applications. Have you done some chemical plants and stuff like that where they've had cavitation or erosion issues too?
Yeah, there certainly have. Obviously, the applications for them are not as great as in the power plant where the pressures are very high, the feed water pressures. But yeah, absolutely. In refining, sour water letdown applications, there are a number of them. There are refineries in our area here where we've got quite a few Lincoln Logs installed. And really the bottom line is any place where you are faced with liquid letdown of 1,000 pounds or more. We've sold Lincoln Logs, Bill, in refining and oil and gas applications where it's not necessarily 1,000 pounds of pressure drop, but where cavitation is an issue and maybe solids are an issue. Kind of jumping ahead of what I was going to say, but this is a trash tolerant design. If I go back and you look here at this conventional way of containing cavitation, you've got a tremendous strainer. So the flow is moving from the outside to the inside, and any particulate's going to get caught around that cage and eventually can plug up to the point where you can't get the flow, the capacity that's necessary. A valve like the Lincoln Log is trash tolerant. We can actually pass 1/10 of an inch per body size. So a 2-inch valve will pass 2/10 of an inch particulate, a 6-inch valve, 0.6 inch. So you can pass a lot of dirt through the valve. Feed water systems, are not dirty, but piping is. So you get scaling, you get things coming off the pipe. In the refining business, there's a lot of dirt in the oils, and so this could be bought strictly for the reason of eliminating cavitation, but also allowing you to pass a certain amount of dirt or trash through the valve. But the real heart of this, and it's kind of hard to explain without slides, but this valve runs flow to open. So it's a little bit different than the conventional way with drilled hole cage designs. You can see the notch plug design, thus where the name Lincoln Log comes from. And there's actually a pressure drop and a recovery. So if you can appreciate, there's a vena contracta and a recovery through each one of these stages. So they're not, any one of the stages is taking the full pressure drop. So there's a percentage through stage 1, stage 2, stage 3. This is actually showing a 4-stage liquid letdown application. And so they're active staging through each one of those stages of the plug. And again, we're taking the pressure drop across each one of those in a percentage, not any one of them taking the full delta P.
Nice.
So with the flow to open design, one of the other features you get with this is that cavitation can never occur at the first stage because it's at the highest pressure. The only place we could potentially get cavitation is the last stage where we're closest to vapor pressure. And at that point, we're as far away from the seating surface of the plug and the seat ring as we can possibly get. And it's also at much lower pressure, so the energy and the potential for damage is greatly reduced. So that float open type design with the notched plug of the Lincoln log serves quite a few different purposes. And what happens is with the pressure drop, as we get to P2, we never drop below vapor pressure. So if this is designed properly, we drop in stages and never drop below vapor pressure. So that we call this design, Bill, a cavitation elimination and not a containment of cavitation.
Yeah, I think that's what we talk about a lot of times, Randy, in our presentations, is the fact that we're not containing cavitation, we're eliminating the cavitation.
That's correct. And as we mentioned earlier, that vena contracta is the point of lowest pressure, but it's also highest velocity. So as we control the pressure drop through each stage, we're controlling the velocity through each stage and reduce the potential for damage from erosion due to velocity. So it's a big deal. It's a tremendous valve. We've got just in our region, Bill, probably 30, 40 customers that we can use as references that are using these in recirc applications, feed water level control, attemperation. So it's just been a tremendous workhorse for us, and we know it's a problem solver. And as I say, we get pretty passionate about it. In these applications, there's a lot of vibration potential. It's a heavily guided valve with the liner that you can see in here. So this is the guiding surface for the plug here. We call it the liner. There's a built-in mechanical feature we call the seat protection. So the first 15 degrees of stroke of this valve, we only allow clearance flow into the first chamber, if you will, and not flow through the entire valve, thus eliminating the erosion due to low lift. So we can't operate this valve below 15% of stroke. And as I mentioned, the trash tolerance. So that's a real quick rundown on this valve, Bill, but I can assure you that anybody that has issues with whether they be drill hole cage designs or other potential solutions for high pressure liquid letdown and cavitation damage, this is the solution, guaranteed.
Awesome, Randy. Exactly, man. You just hit on the major points, which is what we wanted to do today. Cavitation elimination, rugged design, best in class throttling control, reliable tight shutoff, trash tolerant. You mentioned a few other things. I think if anyone's watching this podcast today, Randy, I guess our message is that, if you're a customer has damage to your control valves with cavitation or erosion, please give us a call here at Eastern Controls and let's talk. Perhaps one of our solutions might be that Lincoln log, right, Randy? I think that's the general message.
Yeah, absolutely. We'd welcome any opportunity to discuss problematic valves, and obviously, particularly these that are being damaged by cavitation through high pressure drops in the valve. Yep.
Awesome. Randy Ruth, thank you so much for joining me on my podcast today. I'll catch you very soon, and thanks very much for everyone for watching, and give us a call at Eastern Controls when you have that challenge with cavitation and erosion. Randy, thank you.
Appreciate it, Bill. Thanks. Next stop, Jimmy Kimmel for me.
All right, man. That's a wrap.